I'm Dominic Bill. This is Ridiculous Radios. I added some things to it since I wrote the slide deck, so I've called it Ridiculous Radios because it's more ridiculous. At least one of them is. I'm on Twitter if that's your thing, at DominicJS. I'm not really on any other social media. It's like Clicker works. So I like to put a thanks slide. Oh yeah, I definitely shouldn't sit here. Sorry to the camera operator. I just want to thank some people. I like to put thanks up at the front because one, by the end of this talk, we will be rushed, and two, I like to make it very clear that none of this work is. I mean, this work is all original work that I've done with people at Grayscale Gadgets, but it's based on a work by a lot of people. There's a lot of historical work that's related to it. Not everything in this is something revolutionary that I came up with right before this talk. A lot of this stuff is based on ideas from other people. And various people have helped me get demos together. And the one person who's not mentioned on this is Alex, who is sat in the fourth row and lent me a soldering iron this morning. Here's me using the soldering iron this morning because apparently it was butane and I wasn't allowed to use it inside. So I work for Grayscale Gadgets. Oh, I said I'd skip through this slide, didn't I? All right. I work for Grayscale Gadgets. I write software and things. I am not Tim Brown, as my bio says in the booklet that you've all been given. So if you'd all do me a solid and just cross that line out in your booklets, I trust you all to do that. I'm going to present 4 different sort of projects together in this presentation. They are 2 receivers and 2 transmitters. They're generally radios that are designed in ways that can be built on top of hardware without having to think a lot about radio engineering. They're fairly simple radios to design. We're not building, hack RF or something super complicated, a high quality radio receiver or transmitter. It's a sort of proof of concept, like, can we make a thing work once? And so generally these have all worked once. And I have a demo that even when it works from about a foot away. And given the audience is more than a foot away, that demo is, I'm more than happy to do it live, but no one will be able to see that it works. So you're just going to have to go with me and believe me on that one. So let's start off with a disclaimer. You should know and understand your local laws. I'm not saying you have to obey them. That's entirely up to you. However, a thing that's notable is that car keys, garage door openers, a lot of radio things that aren't Bluetooth or Wi-Fi or whatever, but are unlicensed and you can just have are 433 megahertz. If you start playing around with them, you're very much in the middle of where the UK tetra frequencies are. Tetra frequencies are used for ambulance dispatch and fire engines. And if you miscalculate and get your frequency off by a bit and you jam an ambulance signal, that's really, really bad. So I generally try to obey the law when I do this stuff. My overarching feeling on it is just don't interfere with other people. Don't get in their way and sort of stick to your own stuff. And generally I prefer to build receivers rather than transmitters anyway, to snoop on other people instead of interfering with them. And I will demonstrate, at least one of the transmitters I won't be demonstrating today, but I just have it in video form because it wouldn't be legal for me to transmit it, for me to demonstrate it in the UK anyway, because of the band it's on. So let's start with a scenario. We can get cheap microcontrollers. There are microcontrollers in absolutely everything. They're all over. There are loads and loads of them inside every electronic device you have. Your phone has a ton of them. It's not just the processor. It's the baseband. It's the Bluetooth chip. It's the Wi-Fi chip. It's the thing that controls power delivery to the, both in the charger and at the other end of the cable in your phone when you're charging your phone. I cannot see, everything here has microcontrollers in it. There's a mouse here that has one in it probably. It's radio packs, it's headphones, everything. And they're all running firmware. Most of them running custom firmware designed for their application. And if we can modify that firmware, can we maybe get it to do interesting things? And we approach this from the idea of things like air-gap networks. If we're able to modify the code running on a laptop, can we just use, say, for example, your keyboard controller to receive wireless or transmit wireless signals. Now, a lot of these microcontrollers have a ton of stuff built in. It's not always necessarily used, but it's built in anyway. And these are peripherals for various things. So if anyone's here for Joe's talk earlier, he gave a presentation about how you could run SPI and JTAG and UART and I2C all off the same chip. Now, someone might take that chip and embed it in a product for the SPI functionality, but they don't entirely disable the other functionality. If we can unlock that and use that, then we can get it to do JTAG, or we can get it to do I2C or UART or whatever else we want to do. And so if we can pick up an off-the-shelf microcontroller with an analog to digital converter in it, can we build a very simple radio receiver out of it? So we call this breadboard SDR. It's using a solderless breadboard, and it looks like this. This is on the left-hand side. This is a Great FET 1, which is just a microcontroller breakout board that we designed at Great Scott Gadgets. This doesn't require that piece of hardware. The software I've written works for that piece of hardware, but you could go and build this on top of other platforms as long as it has an analog to digital converter in it. There are 3 wires connecting that to our other circuit board, and I don't know how well you can see that, but those 2 components are a diode and a resistor. Because we're good hardware engineers, we've done a circuit diagram. The circuit diagram shows you the 3 wires and the diode and the resistor. And this is a radio. This is a radio receiver. When we first tested it, Mike's first comment was, wow, it transmits as much as it receives. You really shouldn't use this. Like, this is not a good radio. This will get you in trouble with Ofcom. But you should use this as a base. Like, this is essentially what most software-defined radios are. And then everything else is just to improve the signal quality, the bandwidth, the interference, all these sorts of things is what most of the rest of the board is for. Now, so the way this works is let me explain the circuit diagram first. So the clock signal comes out of the microcontroller. That's whatever frequency we want to tune to. We combine that. Oh, wow. I shouldn't lean on the buttons for slide clicking. I'm sorry about that. Wow. Professional. So what we want to do is we have a frequency we want to receive. We generate that frequency with the clock on the microcontroller. We combine that with the signal coming from the antenna. It goes through a diode. The diode acts as a mixer. It combines those 2. And when you mix 2 signals together, what you end up with is one of those signals shifted downwards in frequency by the other one. So what we end up doing, if we put 433 megahertz into the clock, we get whatever we receive over the air shifted down by 433 megahertz. We sample it with an ADC, and then we put it into GNU Radio. Has anyone used GNU Radio before? Can I just have a quick show of hands? Okay. This is a GNU Radio flow graph. I'm more than happy to talk people through it individually later, but it's probably not all that interesting as a group exercise. Essentially what this does is take the analog to digital converter samples and turns them into audio. And it FM demodulates them and does various data conversion things and throttling speed and stuff like that. And what you end up with is a graph coming out. On the left-hand side here, you can see on the top section of these 2 plots is what we're most interested in. On the left-hand side, there's silence, and on the right-hand side, you can see FM audio being demodulated there, and the amplitude there is the audio that we're receiving. And if you load it up in Spectrum, thanks, Mike, you can see. Try and point at this and see if this works, but this will not come out well on the video. You can see audio here. So this is, we sample the red line, which is where our signal is, on the top plot, and on the bottom plot, we're looking at FM demodulation of that. And one of the things that gives this away is we transmitted this with a little handheld ham radio. And at the end of the transmission, when you let go of the button, it sends out a pilot tone. And the pilot tone is just a sine wave. And you can see that right at the far right-hand side. You have a very regular signal being transmitted. And that's a good sign that we got the signal that we wanted. And Wait. I have to do a microphone thing. Does that work? Hey. Can you still hear me? Wow, that's...
I actually need to turn it off.
I think it's that one that's providing feedback. But we'll see. We shall see what happens. Okay, I should be able to load up this flow graph. Breadboard SDR, narrowband FM. This is the same flow graph you just saw, but it's loading from file because I can't transmit in the UK. I don't have a license. So I'm not demonstrating the transmitter. I'm just demonstrating, and all I did was save the data as we received it. And hopefully, I've just realized I need audio out, don't I?
Here we are, testing on Breadboard SDR, A0NR.
So,
here we are, testing on Breadboard SDR.
So Mike and I were able to transmit with this ham radio, and then with a microcontroller that costs, I think, the chip itself costs about £10, something like that. And we were able to then take two components and build a radio that we could receive ham radio with. So that's a good start. All right. Do the microphone thing again. Awesome. Wait, this should be full screen. Okay, so if you're building a radio in software, you actually don't need much hardware. We can build very, very simple radios. We can build a radio that receives data with only two components. So if you can smuggle a diode and a resistor into your air-gap network, we can probably build a receiver on that end by modifying software without having to smuggle in a hacker ref or a thing that looks like a radio to anyone else. Also, our antenna was just a piece of wire. You'll see throughout this presentation, we're not super picky about the antennas we use for this, mostly because we're working in a lab environment. We're working in the mountains outside Denver in Colorado. There's not as much radio noise as there would be if you were doing it here, and we're generally trying to be good citizens about it and not transmit too much, but we're doing everything at super low power. So scenario 2. We got data into a device that is not, we've got radio signals received by a device that's not traditionally a radio. Can we transmit them back out? Let's say we're in an air-gap network. Can we use a microcontroller to transmit things? So call this clock signal transmitters. It's based on other people's work. Mike Walters, who's sat in the third row, did this back in 2016 at Securi-Tay, I think. I mean, not as a presentation, we just did sat in a room somewhere playing around. But he was able to turn on a remote controlled light bulb using just turning on and off a clock signal. Unsui has done a Funtenna, which was a hack of, I think, a Cisco VoIP phone. And they were able, the group who did it were able to toggle like a very long trace on the PCB so that they could transmit data. And Raspberry Pi FM works in a slightly different way. So, sorry, there are a couple of people trying to get photos of that slide before I skipped it. I will publish the slides afterwards as long as you got photos, it's fine. So again, this is my transmitter. Again, I'm using the GrayFet board because I have one on my desk and may as well use it. And I wrote the software for it, so it's a lot easier to know what I'm doing. That is my antenna. Now, again, this antenna was picked in the same way we picked the previous antenna, which was I reached into a box of wires and pulled one out, and then I plugged it into the board, and it worked, so I didn't replace it. If it hadn't worked, I may have replaced it with one of a different length, but you can do, maths, but why do maths when it works first time? So, how does this work? I wanted to up the game from what Mike Walters did, so instead of doing on-off keying, I did frequency shift keying. I wanted to do it at 315 megahertz, which is why I can't demo it in the UK because that's not an unlicensed band here. But it's really common in the US, and in fact, it's very common for all those things, car remotes, garage door openers, those sorts of things. Now, one thing I could do is what Raspberry Pi FM does. I could just modify the clock generator on the fly. But that's a bit complicated and seemed like a lot of effort and code. But the nice thing about my microcontroller is it has multiple clock generators. So PLL is a phase lock loop. It's just a fancy word for clock generator for the purposes of this talk. is much fancier than that, but let's say that. I could use two of them as long as I disabled my USB interface. So I did that. I couldn't communicate with the device, but I could generate two signals, one at 315 megahertz and one at 315.1. And then I used the SCU. The SCU is just a pin matrix. It just decides which functionality inside the chip is connected to the outside. If you remember Joe talking about things earlier, he talked about how sometimes JTAG is not available on the chip because they are using those pins for something else. That's what the SCU is. It's in almost any microcontroller of a reasonable complexity. You just don't have enough pins around the chip for the functionality that you want to produce. So you use this matrix to switch pins on and off. So the SCU just decides which pin is connected to the output, and now I can switch back and forth between two frequencies just by changing the SCU. The SCU just points to which pin is connected. So I just change which clock is put out at a given time, and I can send frequency shift key data. So this is my car. I load the code, and if you look at the front of the car, it unlocks. This actually worked so well that Mike had not started filming this when I ran it the first time, and because my car uses rolling codes, we then had to capture another code. But you have to be away from the car when you do it. So this resulted in Mike Osman and I running up and down the road outside our office building to get out of range of my car to capture a couple of key presses, then decode them visually using in Spectrum, and then load that into firmware, and then running back to the car to run it again. And so we did that about 3 or 4 times, but we finally got it. Now, one thing that's interesting about this is that my car's center frequency, the frequency it's expecting to see the signal on, is 315.005. But I couldn't configure my clocks that easily. Again, it seemed like a lot of effort to try and skim it by that much. So I put it at 315.05. That's 45 kilohertz off. The frequency deviation between the binary 1 and 0 is only 25 kilohertz. So I'm outside of the range that it's expecting for its original signal. Plus, I couldn't configure it to get the 25 kilohertz range. I got plus and minus 50 kilohertz. It does not care. It absolutely works. And part of the reason is it's a bit like lockpicking. If you go and talk to people about lockpicking, they say the only reason you can pick locks is manufacturing tolerances. We can't manufacture a lock so perfect that you can't, nudge the pins and things like that. And it's the same deal. Why build a radio that is so carefully and precisely controlled that I can't transmit to it slightly off frequency into my car? You've already got rolling codes for security. You want it to work when my battery's low. You want it to work in weird conditions. You want it to work in the presence of noise. So you just build a radio as cheaply as possible. And that means that you don't have super perfect filters, and you don't have rejection of those signals that are just slightly out of band. And as long as my signal is powerful enough, and look how far I am from the receiver, then it still works, and I can still unlock my car. Now, I guess the other reason I can't do this as a live demo is my car is thousands of miles away, and it'd be tricky to get it here and into this building for a very, very quick and dull demo. Okay, so our learning is not only can we build it in software and we don't need much hardware, but if it oscillates like a radio, as a clock signal does, and then it emits as a radio when we plug a wire into that pin, then it's a radio. Just because the microcontroller calls it a clock signal and it's designed to share the clock with other chips on the same circuit board doesn't mean it's not a radio. It's still able to transmit, where it's still able to use data. Use it to transmit data. So, let's go on to our third scenario. How am I doing for time? Yeah, we're hopefully going to make it. So, the scenario is that there will be regimes, there will be governments around the world where they do not allow us to have those analog to digital converters. That first radio relied on us having a cheap analog to digital converter inside our microcontroller, that we could use for a radio. But there might be regimes around the world that limit access to analog to digital converters. And I know everyone's thinking, who would possibly do that? And here's a page out of the US government regulations on export control, and they limit access to analog to digital converters. And in fact, they limit access to high-precision analog to digital converters because they can be used for advanced radio systems and things like that. All sorts of things require kind of converting data between the analog and digital domain. And admittedly, these are incredibly high precision. We're looking at a resolution of 12 bits or more at an output rate of 200 million words per second. So it's 12-bit, 200 megahertz ADC. That is by far and away higher spec than we have on any of the kind of consumer SDRs out there. But it is something to consider that we might not have access to. It's not beyond the realms of possibility that we might have a microcontroller that doesn't have any. So can we use a digital I/O pin? We call this the GPIO pin receiver. So we're going to build a receiver that works, instead of using analog data, uses digital data. And this is where it gets a bit messy. Okay. So there's some theory here, and there are not a whole lot of people in the room, so I'm going to delve into it, but don't worry if you get a bit lost. It's probably that my explanation is bad, and I will happily try again in front of a whiteboard with pad of paper later. This is the first generation that we built, and the silver box you can see at the back is a TV tuner. It's ripped from like an old video recorder, and you can just pull that out, and it will give you a good RF front end. So instead of using those two components that we used on the first breadboard SDR, we're taking a higher quality radio, and it's got some amplification in there, and it's got some good filtering in there. And so we're getting a better quality radio signal out of it. And I would have liked to demo this, and this is actually how we captured the key presses for my key fob. However, a piece of hardware landed on my desk last week, and I thought I couldn't give this presentation without trying to sneak an additional thing into it. So this has not been, we haven't spoken about this publicly yet. We only got it working last week. I only got it working with my laptop yesterday, and I'm going to attempt a live demo. And it may go wrong. Quince. So we name a lot of our experimental boards after flowers. Quince is a flowering plant, don't at me. This board is a comparator, and a comparator just says, is this signal greater than or lower than a threshold? And it currently connects to the RF front end on HackRF. Now, admittedly, this is me using a HackRF to build a low-grade radio by bypassing the good bits of HackRF. But this is because it's a prototype. So in the future, the Quince board will have a whole lot on this, basically where it says Quince, it will have a whole lot of additional circuitry to do kind of analog electronics to shift the 2.4 gigahertz range down to baseband so that we can sample it. But right now we're using the HackRF for that. So the HackRF will tune to 2.4 gigahertz, and then we connect to the expansion header on the HackRF, and we sample that with the Greyfair. There's no data transfer happening on the HackRF. We're just using it as a tuner. So we're only using the analog section of that. There's no SDR happening there at all. On the Quince board, what we're doing is we're sampling using a digital pin. It is either on or off. There is no analog component to this. And that means we sample 1 bit. Now, wrong direction. A problem. We're going to need more than 1 bit of dynamic range to look at our signal. This is really common in SDR. You want a lot of dynamic range. You want as much as possible. People talk about 12-bit ADCs and 8-bit ADCs. Is 8-bit enough for this, that, and the other, and things? So we thought the best solution to show that 8 bits of ADC in HackRF is more than enough for anybody would be to build a radio that decodes things with 1 bit of ADC, 1 bit of dynamic range, and see how that works. So we're going to use a technique called oversample and decimate. This only works in one direction, and this is where the sort of maths comes in. And I'm not going to talk about the maths, I'm just going to show some graphs. But what we do is we take 16 samples like this, and for every pair of samples, we average them to get one in the middle. Now, if you're averaging two numbers, so these are all 0 or 1 bit value. If you're averaging those values, you gain a bit of dynamic range. You can have half values. If you do it again, you can have more values. And so now we have 4 different values, plus the 0 and the 1, I guess. Anyway, we have more values that we can have. And if you keep doing this and keep doing this, you gain for every time you halve your sample rate, you gain 1 bit of dynamic range-ish. It's a bit more complicated than that, but roughly. Now, this means if we have a very narrow signal and we sample way, way wider than we need to, we can then decimate to just gain our signal back, and we get more dynamic range. This doesn't work in the other direction. You can't get more bandwidth by sampling at high dynamic range and then working the other way. It only works this way. So it looks like this. This is a slightly more complicated flow graph. But essentially this is doing it's doing a lot. But this is the main block that we care about here is the, where is it? We've got at the top two, you can't even read them from where you are, but the top two on the right, we have a filter that decimates and we have a rational resampler that also decimates. And so what we gain there is dynamic range as we lose, we lose bandwidth. But we don't care about bandwidth because what we're looking at is a 1 megahertz signal. Now, what we're able to sample at, because it's a digital I/O pin, digital I/O pins are used for fast binary interfaces. So we can sample at 100 megahertz. So we get 100 megasamples a second, but we only need 1 megasample a second, so we can decimate and we gain a number of bits of dynamic range in order to receive things. So using 1-bit sampling, it's time to do the demo. So I'm going to switch microphones again. Hey, okay. I've only run this once. I've only had this work once. So, everyone, hopefully it works for me. Sure. That's not what I want. I've just got to copy and paste a command. So I'm just tuning the HackRF at first to a frequency. It's just going to dump samples into a file somewhere. I'm not going to use that file for anything. Then what I'm going to do is use the grapefet that's attached, and I'm just going to use the logic analyzer function of it to sample those pins as quickly as possible. Right now I have a limitation of pi USB and my firmware. That means I only get 17 megasamples a second. I just need to do some firmware hacking to get that up to 100. And then I should be able to... Oh, wait. Then I turn on a device that should connect to my phone. And what we're using here... Come on, connect. Excellent. And then I'm just going to very briefly generate some traffic. Okay, so that's generated some traffic, and it's all being saved to this quince4.dat file. So let's kill that off. Let's go to our complicated flow graph. Now, what this is going to read is that file that I just wrote. Oh, I guess I can turn my headphones off. That's going to read this file that we just wrote, and it's going to output to a file called temp-dmod. So I'm just going to run this. Now, what you'll see is in the top graph, hopefully, there you go. This is doing what's called burst tagging. It's finding packets in the data. So if you see these all look fairly regular. These are all the packets that were transmitted that I was able to pick up. These are Bluetooth packets. So what I'm doing is simultaneously, I'm able to receive 17 megahertz of data and then take that 1-bit value and convert it to enough bits to pull out Bluetooth data. But because that's done in a filter, because that's done for a specific frequency, I'm able to do it 17 times, once for each Bluetooth channel in that 17 megahertz chunk. Once I get this up to 100 megahertz, I'll be able to do it for every Bluetooth channel simultaneously, and be able to sniff all Bluetooth connections within range simultaneously, just using 1-bit ADC sampling. So, and just to hopefully prove, if I output my data into a file format that is accepted by the Ubertooth tools, because I happen to know the developer of both, because it's me. And what you'll notice is I was able to pull out all these Bluetooth packets, and this LAP is the address, is the MAC address of my Bluetooth headphones. And I'm able to pull all these packets out. Now, the channel information and various on the clock information is all wrong at the moment because it's just a proof of concept. but I was able to accurately receive and decode Bluetooth packets, but I was only using a digital I/O pin and no analog to digital converter at all. So we don't even need an analog to digital converter to digitize radio. How's that? Excellent. Oh, wait, I have to go back and keep the microphone away. Dun, dun, dun. All right. How am I doing for time? We're all right. Oh. Interestingly, my slide clicker has ceased to function because I started playing music. So I'm going to have to use the old method. So 1 bit of dynamic range is more than enough for anybody. Everyone can stop complaining about 8-bit ADCs. Okay, final scenario. There's a thing called pseudo-Doppler direction finding. There are pieces of hardware called they're used for finding radio signals. So the idea of them is that you want to be able to track down people who are transmitting. Now, in general, mostly who you want to track down are people who are interfering with you. Ham radio operators use them a lot. Generally, if you transmit on a ham radio band accidentally and without a license, ham radio operators will track you down quicker than anyone else. They're so good at it because they care, very passionate about it, passionately. So Mike developed a pseudo-Doppler direction finding rig. We call it an antenna switching board. It's also known as an opera cake because we like food. So can we find some way to subvert it? So I'm calling this direction finder to direction hider because I couldn't think of a better word than hider. I'm not even sure it's a word. So I'm going to see if I can make my phone be my clicky thing again. Okay, let's try this. Oh, no. All right, pseudo-Doppler direction finding. Not only am I not good enough at explaining things to get it out in the time I have, but it's already been done by Mike Osman and Skylar at ShmooCon a couple of years ago. There's a link on this slide. Go watch their video and they'll explain how pseudo-Doppler works and how it works with our board and how we're able to attempt to find things with it. But essentially, this is the opera cake board. It's just a bunch of ports and it switches antennas, so you can have an input coming in and it switches to an antenna and you can electronically switch your signal between antennas. It's really, really useful for direction finding. It's also useful for if you set up a ham radio rig and you want to switch between antennas that you're using on a given frequency, or you want to switch in different filter banks and things like that. So let's talk about radio again, if we have to. Phase shifting. So does anyone know about has anyone studied radio things, different forms of modulation, phase shifting, any of this stuff? Hands up. Okay, well, I'm going to try and say things that you understand, and I'm not very good at that. So you should look this up in a textbook if you really want to understand it, and I can recommend some textbooks to properly understand it and understand the maths of it and things like that. I really don't want to put maths into my presentation, so I didn't. Phase shifting is where you take a signal and instead of changing the frequency or the amplitude of the signal, you change where you are in the waveform at a given time. So phase shift keying works by making phase jumps in the signal, jumping from one point of the signal to another. When we're doing direction finding, what we do is we take multiple antennas and we switch between them rapidly and usually in a circle. And that gives us a phase shift based on where you're coming from. So essentially what happens is where you are in the waveform is different at the two antennas at the same time. So you generally want the size of your array to be about, the distance across your array to be about a third of your wavelength. And that means that if you rapidly switch from one antenna to the other, you'll see the same signal, but you'll see it just slightly off from where it was. And you can use that to try and calculate the direction. But we can make that happen too. We can induce a phase shift, and therefore the direction finding rig is going to think it sees a phase shift, but it's actually the one we control. So this is a diagram I made in a hotel room. At the time, I thought it explained it. So everyone understands phase shifting now, right? But essentially, if you have two different lengths of cable or two different placed antennas, the waveform, the electricity that you're transmitting, or the electromagnetism that you're transmitting, will reach them at different times, and therefore different parts of that wave cycle. And so what we can do to introduce a phase shift into something is have two different lengths of cables. These are often called delay lines. I spoke to someone about this about a year ago, and they said, oh yeah, I've used delay lines. I used to work in fiber optic. We used to just bounce data between Silicon Valley and Los Angeles to just induce a delay into the data, because that's long enough for a delay line at the speed of light. Or just like 30 kilometers of coiled fiber optic, just as a delay loop in their lab. But we do it with RF. We do it at 2.4 gigahertz, and therefore a quarter of a wavelength is about 3 centimeters. And therefore, these 4 cables that hook up to my opera cake are all 4 centimeters off from each other, 3 centimeters off from each other. And that means I can induce a phase shift by cycling through them. So, whole point of me presenting from Google Slides was that this video would work, and we shall see what happens. So, this is a direction finding rig. This is one we set up for 2.4 gigahertz. You can see in the glass the 4 antennas. They are at 4 different locations, and they're separated by roughly a third of a wavelength, and that feeds into the opera cake, which feeds into a hacker F, which is attached to Mike's laptop. This is slower than I thought. Come on. So that's Mike's laptop. He's running his direction finding code on it already. This is my laptop. This is my transmitter. And I have my delay lines on it, but I'm not using them yet. I'm just going to start transmitting just some data. I'm just going to send some data out. And I didn't pause it quite the right moment, but you'll see on Mike's display in the top right corner, there's a sort of fuzzy blue dot. That gives us a direction from his direction finding rig to my transmitter. And we are able to kind of use that, and if you calibrate it properly, he knows where the transmitter is. So what I want to do is make it so his software no longer receives it correctly. So what I do is I just start looping through those 4 different cables at different lengths, and you'll see we now have almost no idea, and this was bouncing around all over the place, so we now don't have any idea of the direction of the transmitter. So we're able to use exactly the direction finding rig that he's using to detect us to subvert his detection. So you see it's jumping all over the place. Oh, that's really not what I wanted to do. There we go. So adding a phase shift, circumvents Pseudo-Doppler. Now, this is really going to destroy your signal if your signal relies on phase shifts and things like that. But if you're using on-off keyed or frequency shift, then it's not. You can get away with it. So, and this is going to be very quick because I'm running out of time, and this is the demo that only works from about a foot away, so I'm not going to do it because Graham's already here to give his talk next. But since we can modify the phase to subvert the direction finding, can we take a signal that is being transmitted and has no phase component that we care about and add a covert channel over the top of it? Can we add on a phase shift keyed signal to an existing radio? So I'm not even talking about like building an SDR. I'm talking about taking our opera cake board, which looks like this, and a microcontroller to control it, and no radio, or just take an existing radio that we do not care about. It could be a handheld ham radio device. It could be any radio you have. It could be a Wi-Fi device. It could also be a Bluetooth dongle. So this is my transmitter. This is a like $3 Bluetooth dongle I picked up from Amazon. We cut the trace to the antenna on the circuit board, and we just soldered on a cable. And then we called out one of the test functions that they left in the firmware in the thing and got it to just transmit a signal on a single channel. And so this was my transmitter. And so all I'm doing is transmitting a 2.4 gigahertz carrier out of that. And then externally, I'm just taking the opera cake board and I'm adding that phase shift. So this is in Spectrum again, a great tool for this sort of work. And you can see this is a phase plot at the bottom of the signal we see at the top. And these just show us the phase jumps that are happening. And these are kind of instantaneous phase jumps, like here, and here, and here. And so we're able to create instantaneous phase jumps by switching between different lengths of cable on the upper cake. So we have 2.4 gigahertz. We can add phase shift keying. We can actually switch these 11 million times a second if we want to. That's how quickly our switches work. They work faster than that, but 11 million is going to be really convenient in a minute. Direct sequence spread spectrum is actually just really, really fast phase shift keying. So we could generate a DSSS signal at 2.4 gigahertz at 11 megabits. Now, does anyone know what an 11 megabit DSSS signal is? Graham? Wi-Fi. It is Wi-Fi. Wow. There you go. So we're able to produce a completely fictional Wi-Fi network from a Bluetooth dongle and an antenna and 2 lengths of antenna cable that are different, off by a half wavelength between the two, and switch back and forth between them at 11 megahertz using an antenna switching board and a microcontroller to generate a Wi-Fi network that never existed. It is completely pointless, but it's really good fun to do these sorts of things. This works from, guarantee, a distance of about a foot. And it really, really does not work at conferences when everyone's got Wi-Fi and Bluetooth going. So it is not possible. While I was able to transmit from my phone to my headphones and receive Bluetooth packets in the middle, for some reason this is just not powerful enough to really get to phones. But we have managed to pick it up in quiet environments in our office. And you can see one of these is my phone and one of these is my boss's phone, Mike's phone. And we're able to receive the same network on both. So, an external modulator, or antenna switching board, can add a covert channel to any existing radio if you can connect it and your covert channel does not interfere with the existing underlying radio signal. Again, thanks to all these people who were involved. Thanks to Alex for lending me a soldering iron this morning, even though I didn't run the demo that I needed to solder this morning. So that was potentially a waste of time. And I will not take questions because it's 10:02 and Graham probably wants to get set up for his talk, but I will take questions outside or just find me around. I'm very approachable. Just come and ask me questions if you have them. You can find me on Twitter or Great Scott Gadgets on Twitter, and all of the code should be on one of those 2 repositories to implement any of these. So if you want to go ahead and implement these radios yourself, do it legally, do it safely, don't interfere with ambulances, and have fun with radios. Thank you very much.